He is from Christian Alberts University from Germany, and the topic of his team is a generator theorem with applications to queuing systems. I'm sorry if I pronounce in the wrong way. You do it better. You're welcome.
Yeah, thank you very much for the opportunity to talk here. Actually, the generator theorem I will talk about is more or less the same that Marta Tyran-Kaminska talked about a few minutes ago. But I'm from a functional analysis background, so I had a little bit of a different view on the theorem. And my main motivation was to apply it to queuing systems. So I will start by recalling the notion of RL spaces for people maybe not who have not seen them before. Basically, an RL space is a Banach lattice where the norm is a positive functional on the positive cone. And basically, there are a few different examples for such abstract Lebesgue spaces, and the usual example is just L1. So if you have never seen them before, you always can think of some kind of L1 space on a suitable measurable space or measure space if you want. Another thing is if you have already an LL space given, then the Bochner space L1 with values in that LL space is also an LL space. And another example might be the measures of bounded variations. So it's just a notion to generalize L1 type spaces, basically. Some facts about RL spaces that will be important for us later on. As I said, L1 spaces are AL spaces, but also the converse is true. So every RL space is less isomorphic to some L1 space on a suitable measure space. So they're interchangeable basically. But we just need the algebraic property here for what will follow. So I will talk about AL spaces. Another thing is, or another fact about RL spaces, the dual is a so-called AM space. It's not important what that is at the moment, but this AM space has an order unit, which is basically just the one function if you're working with L1 spaces. So, but you can define it abstractly as that kind of functional here. Okay. So now, we have the same situation from Martha's talk, and to make things worse, I use a different kind of notation. So I will try to translate it on the fly. So we have two LL spaces, and we consider the product with this norm, and then this product space again becomes an LL space. And we are interested in this kind of space here that also turned or was also seen already in Martha's talk. Now we have some kind of maximal operator, which is just a closed operator on the space E, which we call the state space. And we have a boundary space, that's this del E space there. And we have a surjective boundary operator. And then we can consider this operator A naught, which also was part of Martha's talk. Basically, this L here is, I hope I can write it without, no? It's basically this operator here from the talk before. And an example that one, so that one can get an impression what that means actually. So if you consider a bounded domain with a sufficiently regular boundary, for example, Lipschitz boundary, we can choose E as L1 of that domain. And as a boundary space, we take just the L1 space on the boundary. Then maybe we can consider the Laplacian on some suitable Sobolev space. And then we know from basic theory that we have a trace operator of that form. And if we consider A not with respect to this trace operator, we just get the Dirichlet Laplacian. So that's the way one models boundary conditions with this framework. And we also consider operator matrices. We have also seen before in the talk. Here we just have the matrix we all have already seen. And now we have a control operator. Basically, we want to control the boundary values, and we do that via such an operator phi. And then we can consider the operator A. And major question was when this operator A, when does this operator A generate a semigroup, substochastic semigroup, and so on. And I introduce another operator matrix of that form. And then we set cal A basically just as the sum of this matrix and this matrix. And this allows us to observe the following thing. If we consider the parts in this smaller space here, like in the talk before, then they are isomorphic to these operators here. And so we know that if this operator matrix generates a semigroup, then we also get a semigroup generation from this operator we are actually interested in. And the stochastic properties also translate directly. And now, this theorem from Greiner from the paper mentioned in the talk before is important for the theorem. Basically, it says if we have a value of the resolvent set of A naught, then the domain of the maximal operator decomposes into the domain of A naught and the kernel of that operator here. And if we restrict L to this kernel, then it's an isomorphism. And as already seen before, we can invert this isomorphism, and this is called the Dirichlet operator. Here again, I think it was D lambda in the talk before, not quite sure. But this is this operator we have already seen. And in our example, it says if we have a value that's not contained in the spectrum of the Dirichlet Laplacian, then we can show that the Helmholtz equation to any boundary value in L1 has a unique solution, and the solution operator is basically bounded. That's what that means in this example. And now, I present the same theorem basically as Martha Thurin-Kaminska did in the last talk. I suppose that the boundary operator is surjective and positive. We assume that the control operator is positive and that this operator here is invertible for each lambda bigger than 0 with positive inverse. In practice, one usually can show that the norm of that operator here is strictly smaller than 1, and so you can just use a Newman series argument basically to show that in practice. Then I assume that A naught is densely defined and resolvent positive, and we assume that kind of estimate here that also turned up in the previous talk. If you write it down for some L1 space, it just means you're integrating basically this function here. So that we have already seen that. And the statement of the theorem basically is that this operator matrix generates a positive semigroup on the product space. And you can give it resolvent explicitly in terms of this resolvent and this operator here. And as already seen in the talk before, if you have a stronger estimate here at this point, then you also get stochastic properties. And if you have even equality, then you get a stochastic semigroup on the product space. Okay, let's prove that. And for the proof, I basically need just two very well-known theorems. The first one is a version of the Hille-Yoshida theorem. Basically, it works as follows. So we have a closed densely defined operator. That's no surprise there. We assume that it's resolvent positive on some LA space, and we assume that we got such an estimate here. And then the theorem says, okay, then we get the generator of a substochastic semigroup, basically. And the other theorem I need is a Miadera-Vogt perturbation theorem by Vogt from 1989. And it basically states that if you're given a generator of a positive semigroup and you have a probably unbounded perturbation that is positive, such that the sum of both operators is still resolvent positive, then the sum generates a positive semigroup as well. And now one just has to combine the two theorems to prove the theorem we have seen before. First observation is Carl A naught is closed. That's just a direct consequence of the closedness of this operator A naught and the continuity with respect to the graph norm of L, basically. Not L lambda, but L. And also Carl A naught is densely defined, and one can explicitly write down its resolvent. So we see from that formula there that Carl A naught is resolvent positive, because this is a positive operator by assumption, and this one here too, as a result of the assumption on L. And in this in the second step, one has to understand this estimate here, because one can write this term here just as I take Carl A naught, test it against some vector in the product space here, and then I test it against the one function in the dual of the product space. And this is the same as writing that down. And now you see probably where it's going, because now we just can apply this Hiller-Yoshida type theorem to the operator A naught, Carl A naught, and we get a substochastic semigroup on the product space. And in the second step, we are interested in the operator Carl A. So this is just a perturbation of that Carl A naught. So here comes the perturbation theorem into play. So you can easily calculate just by matrix multiplication that this operator has this form. And furthermore, we know by assumption that this operator here exists. So you can just write down a formula for that operator here, for this inverse of that operator directly. And this is again a positive operator, because we are by assumption all these operators here are positive. So this is a positive operator as well. And we have already seen that this is also a positive operator here. So the composition of both operators is also positive, which means that the operator Carl A is resolvent positive. Okay, and now we can just combine our findings, basically. So we know that A naught plus B naught, which is A, is resolvent positive. We know that Carl A naught generates a semigroup on the product space. And we know that our perturbation is a positive operator. So Vogt's theorem just yields that this operator here generates a semigroup on the product space. And when we are now interested in the operator A, then we can just watch the part of, or look at the part of this operator here in this space Carl E naught, and then we get the same result basically for the operator we are interested in. Okay, now I already said my main goal was to apply that generator theorem to queuing systems. So I just took one very basic queuing system from literature, from Haji and Radl. They considered in 2007 the following queuing system. So basically the idea is you just got two machines with a buffer, and you get some kind of input, maybe some kind of metal or something, anything that the machine one can work with. And with probability eta 1, it goes to the buffer. And with a probability of Q1, it goes back into the same machine to get reworked, basically. And this buffer here has a fixed capacity, namely N. And the second machine takes the objects from that buffer and works on them, basically. And with a probability of eta 2, it gets output the material, and with a probability of Q2, it goes back into the same machine and gets redone, basically. And what is important is if this buffer is full for some reason, maybe machine 1 produced much more than machine 2 could produce in the same time span, and then machine 1 stops to produce anything and waits until the buffer is until there's until the buffer is not full again. So basically one can model this with probabilities here. It's not so interesting, but if you're interested in what these probabilities mean, basically the probability that at point T, there's machine 1 runs, and the buffer is empty is modeled by this quantity. All situations between the extremes are modeled by this probabilities. And the situation that the buffer is full is modeled by this probability. And X is just the elapsed service time of each of these services. So this is the way it is modeled. And that yields to the following set of equations, if you model it like that. Here, eta 1 and eta 2, we all have already seen this mu here is just, basically a way to describe the production rate of the second machine. And probably you noticed a lambda that turns up here. That's just related to the speed width that the first machine is producing. So you get the following equation system, and you have boundary conditions also. So you have to say what happens if you start to work on a new piece, basically. So that gives you your boundary conditions. And then you have the following initial conditions. Yes, at the first, at t equals naught, the buffer is empty, and the machine produces. The first machine starts to produce. So this is the most interesting initial condition for that system. And now one has to fit it into our framework to, basically to use the theorem. So one just considers the following space, just C times such an L1 space. And on our boundary space will be Cn plus 2. And then, one writes down the differential operator, which is a little bit messy, but it just models the system, basically. So you got some kind of functional occurring and some differential operators here, working on the Sobolev space. So nothing fancy, basically, it's just a little bit messy to write down. And as a boundary operator, one chooses just the evaluation operator in the zero, which is also no surprise, because let us reconsider our boundary conditions. That's exactly what's done here. Okay, so you just have to describe the control operator, and the control operator takes this form. Also, you just have some multiplication going on here in the first variable, and then you have this functional, which works basically then on these functions here. And then Gupur proved in 2003 that the operator A, just basically written down in this form, generates a substochastic semigroup, basically by calculating all by heart. But we can use the generation theorem of Kaminska and Gwiszcz just to show that this operator generates a substochastic semigroup on the space E. So already Haji and Radl observed in their paper that L is obviously surjective and positive, and it's also continuous with respect to the graph norm on the domain of the maximal operator. That phi is also positive. That's also very easy to see. And this operator here, they really calculated basically. So you can see it is positive by calculating it directly. And that A naught is densely defined, and resolvent positive densely defined is also quite clear. And resolvent positive, you can calculate that as well. So you just need to calculate basically the resolvent of that A naught. And the crucial estimate one has to check is then the following. We want to see that it generates a substochastic semigroup. So our aim is to estimate the sum of these both terms basically. So one just can calculate them directly. And if one sums both terms, then the most things cancel out basically. You can see here, this term cancels out with that one. What else? This term cancels out with that one. And you are left with these terms. And the sum here is always 1 because that was the probability that the second machine outputs the material, and that was a probability it retakes the material. So the overall probability is 1, obviously. And then a lot of things cancel out, except for the last summand of that sum. But if we calculate, or if we add this one to that last summand, we just get this. And our P is a positive function, and this is a positive functional with a negative sign in the front, so we can just estimate it, like that. And so basically we proved using that generation theorem that A really generates a substochastic semigroup. Okay. So another thing that is usually done in this papers in queuing theory is the asymptotic behavior of the semigroup involved. So I just recall the notion of an atom in such an A space. Basically, an atom, it's in vector is called an atom if its principal ideal is one-dimensional. And when you go back to the case of L1 spaces, then it's pretty obvious what that means, basically. So if you have a measure space and some atom of this form, then the indicator function of that set is an atom in this sense. So it's just translating the notion of the atom in the measure space to the L1 space, basically. And we dealt with the following space in our example, and the norm on the space is just, again, a L1 combination of L1 norms of that form. So this is this space with that norm is an LA space, and it's easy to see that this vector here is obviously an atom in the sense of this definition here on top. And then you can apply a proposition proved by Gerlach and Glück in 2019. They proved the following theorem, basically. If you are in an LA space with an atom and you have a substochastic irreducible semigroup, and you know that the semigroup possesses a non-trivial fixed vector, then they showed that this semigroup operators converge strongly to rank 1 projection, and you can write it down basically directly as a result of the irreducibility. And what's worth to mention at that point, Haji and Radl in their paper used a version of the RBLV theorem to investigate asymptotic behavior of their semigroup. This result here from Gerlach and Glück does not rely on the RBLV theorem. It's just a pure lattice theoretic arguments that are involved. And my time runs up, so let us just prove how to apply that theorem to our example. Now, first, I already mentioned that space is an RL space with an atom. Then we proved that A generates a substochastic semigroup. That was just as a result of the generation theorem we proved. And then it is shown in the paper of Haji and Radl that this operator here is column stochastic, and then they got some kind of characteristic equations that tell you that 0 is contained in the point spectrum of A. But as we all know, if you are in the kernel of A, you're basically in the fixed space of T. And okay, if 0 is a point is in the point spectrum, then you find a eigenvector which is non-zero by definition. So you get a non-trivial fixed vector of the semigroup. And finally, Haji and Radl already showed that this solution semigroup is irreducible. So the theorem of Gerlach and Glück yields the claim. And that's the point where I want to stop. Thank you very much for your attention.
Thank you, Alexander.